Okay, so we have an exam tonight, 7 o'clock. I will see you there. Starting out, a reminder that the entire chapter 5 is just this slide. So we had three types of motion. Translation, where there is no rotation of the body. You can have curved path motion, you can have straight line motion. And you saw that in the case of those linkages that kind of go like this. Same length, and the bars sort of, they're both going at the same velocity. And this is actually in translation. The second type of motion was rotation. And we've done a lot of cases where we've done fixed point rotation looking at an object that is connected to another object. One end is translating, one end is rotating, and then in between you have a link. And so one of the things to remember with all of this is that you want to carry through with this sort of analysis. So you want to describe things in translation and rotation before you move on to general plane motion. General plane motion is what we spent most of the course, or the chapter 5 on. We looked at absolute motion, we looked at relative motion, we looked at relative motion with graphical approaches and relative motion with vector approaches. If at this point you're still convinced that graphical is better, I am unsure what to tell you. Okay? I really think that a vector approach is often much stronger when dealing with these particular types of problems, especially when you get down to the acceleration part. So in the homework, you're going to have questions 4 and 5. You have acceleration. You can do them, and this is a very quick sketch of the graphical approach. You can see how complex it becomes, normal, tangential, acceleration B, acceleration A. All of that is there. They can be done using graphical approaches. I would not do it that way. Often, it's a lot easier to just say minus omega squared r alpha cross. However, and I got a question about this on Piazza today, draw diagrams. It doesn't matter whether you get points or not for them. They will help you in terms of solving the problem. If you do not draw the diagram, you're going to miss something. And if you have nice colored pencils and you can put red forces and blue boxes, that's a lot even better. All right. Quick return with a stomp. Okay. Oh, instantaneous center zero velocities, don't abuse them. You don't have to. If you have to, you solve it as a vector and then you tell us where the instantaneous center is. That's pretty much it. That's my sort of summary on that. So where are we going today? We are done with chapter 5, and now we're going to start to deal with the problem of what happens when you have size and mass. So rigid bodies have size and mass, and everything we did in chapter 3 kind of dealt with the mass component. Now we have to worry about rotation of a body and the potential that there is going to be some sort of force associated or offset. So if I have a small mass element, which I have defined on this ring, dm, I can say that the moment of inertia, is equal to r squared dm. This is always I. You cannot ever have a negative moment of inertia because you have r squared, which is a positive quantity, dm, mass, which is not negative. But what's interesting here that this is not an absolute value. Mass is an absolute value. You go somewhere, you have the same mass. Moment of inertia, on the other hand, is going to depend on how far the mass is from whatever point of interest there is. So here, for example, I have an origin, and I've defined what looks like just a circular section, say a pipe section, and the center is there, and I'm defining a moment of inertia there. There's nothing to stop me from defining a moment of inertia out here. And so every moment of inertia is going to be pretty much dependent on how you set them up. If you start to deal with bodies with variable mass, so where rho is defined as density, which is mass over unit volume. So kilograms per cubic meter, and if you have steel versus feathers, you get very different results. You can say that dm is equal to rho dv, and for the purpose of this course, I'm going to start putting a slash through my v's because those will be volume, not velocity. So I can say I is equal to the integral of r squared dm, which equals r squared rho uv and if rho is constant, which we're going to deal with mostly, you end up with I equal to rho r squared dv. And so it then becomes an entirely volume-based approach and doesn't depend on variable density. That's a sign. The important thing is you got to know what this is and where it comes from. In the end, you're going to have a lot of simplifications that allow you to get things moving. So, for example, I think that my reference to the Simpsons is going to be lost here, but there's a very old Simpsons episode where an inanimate carbon rod became person of the year. And the item of greatest interest in this course is a long, slender rod. And so you will learn what the moment of inertia is, and you will have to know. We can integrate and do this in a number of different ways. These are not terribly important. If I look at a rod or a disk element of radius r, thickness dz, I can say dy or pi y squared dz and just integrate away. If I want to look at a shell element, it's dv equals 2 pi z. All of these sort of definitions are useful to sort of recognize what they are. We don't use them. And so I don't spend a lot of time talking about them or the derivation anymore. I used to. It's more fun to do that, but it's not very helpful. Okay. Wow. Okay, good. All right. But you do have to recognize there's a whole bunch of charted examples that give you the I for various bodies. So these are volumes. So for a hollow shell, you have m over 2 r1 squared, r2 squared. For a plate, you have m over 12 h squared plus w squared for another plate, but at the end, you'll notice that was what we started with. Define r here, or define r here, and you change what your m over, or your moment of inertia. And in that case, it's m over 12, 4h squared plus w squared. For a shell, you'll get a different number, and then a solid. And so as you're going through all of this stuff, you kind of have to make sure that you recognize what's going on and some of these things. All right. I really kind of, this is all definition. We just sort of go through definition and we kind of sort of define things and then say, ignore all of this and we just give you the tables and we say, here's the important terms that you have to know. So let's at least try one integration. We have moment of inertia for a constant density cylinder. Its center of mass is G, and it's defined there as the origin. I have X, Y, and Z. Okay. And I can say that TV equals 2 pi L R dr. So I'm just taking, we'll integrate in small shells and integrate all the way across, L being just the total distance across. dm equals rho dd, rho 2 pi L r I is equal to r squared dm integrated, and then you just put terms in. If you sort of do the calculation, you end up with 1/2 rho pi r to the 4th L, which if you substitute in for the mass, you end up with 1/2 m r squared. Okay, again, it's the derivations of these are not going to be your primary work. It's the use of these things. And so I'll spend more time later looking at particular cases. But as far as this is concerned, oops. Not very exciting. What is exciting is this. I didn't include it. Okay, so what I am worried about, and I'll use my last year's notes here, is this right here, uniform cylinder rod. So there it is. You're going to spend a lot of time, and you will recognize 1/12 ml squared, and that's with respect to the center. If you shift it, it's 1/3 ml squared. One of the questions you should be having at this point is, how do you do the shifting? Do you just integrate every time? And so, you know, if you have a whole bunch, if for example, I want to make the light cylindrical, you have to integrate to the midpoint somewhere here to calculate what's happening in return. All of this is really just, oh, and this is table D4 in the text, by the way, so you already have this. None of this is this is just sort of fundamental to start. So these are a whole bunch of different things. as you sort of do these shifts, you have to be aware of how you're doing it so that you can sort of substitute things in. And the way to sort of do that is one of the things that you do have to know, which is the parallel axis theorem. So with the parallel axis theorem, I know that I is equal to r squared dm. So already we've done this before. We've kind of that's the starting point of these lectures. But here's an element that's sort of shifted. I've got 2 points of interest. I've got a point A and a point G. G is, say, the center of mass. A is just some arbitrary point of interest. So if I do that, I can say I is equal to the integral of d plus x prime squared plus z prime squared dm. And I'll try and do this so I don't lose this. D is here, z prime. No, what? So this is not off the center. This mass is a distance d from the center. It's a distance, or d plus x prime, and a distance y prime, and it's at the z equals 0 line. So z prime, z are both 0. So if I have an r squared, I can write that in this form right here, which is d squared, d plus x prime squared, y prime squared. Okay, and that time I turned on the thing. And I is equal to the integral of x prime squared plus z, or y prime squared plus 2d y prime plus d squared dm. So I'm just taking all of the terms that I have, just combining them, putting them together, and I end up with that expression right here, which is kind of neat. It's okay. But when I do the integral about g, or about with respect to g, I can say that x prime squared plus y prime squared plus d squared dm plus 2d x prime dm. So all I've done is separate out the integral, and in the process of separating out the integral, I have just gotten rid of, or I've taken this term out here, which is 2d y prime, and hey, there should be a z prime. Or it's, x prime. That's x prime. Now, with any type of body, if I do it about the plane of symmetry, and that's plus x prime, and this is negative x prime, I will have equal and opposite areas. So if I do the integral over the mass, this last term goes to 0. And so in this case, I is equal to the integral of x prime squared plus y prime squared plus d squared dm. Now, the funny thing is that x prime squared plus y prime squared gives me I sub g. So if I reference everything with respect to the center of mass, I can say this point here is r squared, prime squared. And this last point is kind of weird, but it's there, it's a constant length. And so I get out of that the integral of r squared dm plus d squared dm. And this first term is I sub g, and the second term is md squared. And that becomes the parallel axis theorem. And the parallel axis theorem is going to be very important to you. For the rest of the course, you are going to use it on a weekly basis, and this is how you shift things from the center of mass So if you remember with the long slender rod, if I pinned it at the center, I had 1/12 ml squared. If I shift it by d, which is 1/2 L, I'll get a quarter. That quarter ends up adding in 3/12, I get 4/12, and I get a 1/3 ml squared, which is the term I get when it's pinned at an end. And if I want to shift anywhere else on the rigid body, I can do that. And so it's really important to think about it in that perspective, that all of these terms, all together, everything is going to be referenced from the center of mass. So what you need to know is not necessarily a whole bunch of centers or moments of inertia. You do need to know moments of inertia for a long slender rod, I think a disc, and maybe a plate. And after that, you can shift to any point on the body as long as you sort of think about it. So what that means is I have a body, I have G here, and I have A here. And its perpendicular distance is D. IA equals IG plus MD squared. And I can just shift arbitrarily to any point anywhere without having to look up tables and without having to redo the integration. However, IG does not equal IA plus MD squared. You can't do the reverse. You can say that IG is equal to IA minus MD squared, if you want to do that, but there's not much call for it. So this is something that you will see in the crib sheet. This is something that will be important as you're sort of continuing for the remaining 24 or 15 lectures. Okay. So there's one other thing. This. So I steal a landing gear from somebody and I put it on the site, or on this note. And the reason why I think this is Short Brothers, but if you look at the complexity of an object like this, and you are then asked to create some sort of analysis, often you will find tables of values in the commercial literature that describes it in terms of a radius of gyration. And so essentially says that this complex machinery is the equivalent to this. And to make things very confusing for you, we use K for that radius of gyration, and I often use a K sub G that is going to describe what that is. So IG of the landing gear here is mkg squared, and this is the radius of gyration. Ugh. Questions? We're still sort of deriving things at this point. Nothing's sort of happening yet. Let's see if I have. So there are two important concepts. You need to recognize that your definition of this is r squared dm, and that tells you, for example, that the units on this are kilogram meter squared. Separately, you need to know the parallel axis theorem. And so you have some sort of object, A and G, and the distance d away, IA equals IG plus md squared. The other thing that you need to know is the radius of gyration. So you will see as you look, if you've already looked ahead at the final exams, we will give you certain things. We might give you an object that is, we say the radius of gyration is 1 meter. We may say to you, this is a pinpoint on a long slender rod, and we expect you to find what that is. And so you end up with sort of these odd shapes where you have a center of mass here, and then you sort of convert it to a hula hoop of radius r. And IG equals m kg squared. And kg, again, is not going to be a spring constant, and this is going to cause a lot of trouble for me later, is just the radius of gyration. And it has units of meters. The other thing that you often have are composite bodies. So say, for example, I have a long slender rod attached to a disc. And so they're cantilevered together, and they're attached to a wall. And I have r of the disk, I have g of the disk, I have g of the rod. So let's say that Lg of the rod is equal to 0.3 meters. Mass of the rod equals 3 kilos. Length, or the radius of the disk, is equal to 0.2 meters, and mass of the disk is equal to 2 kilograms. If you want everything with respect to point A, which is something you often do, you can shift everything at this point. Length of the rod, Lg of the rod is really going to be L over 2, so I just leave it at that. And I can say that IA equals Ig of the rod plus mass of the rod times length of the rod to G squared plus Ig of the disk plus mass of the rod, or mass of the disk times length of the rod plus radius of the disk, quantity squared. So for this first term right here, length of the rod G is L over 2, and it goes from here to here. The second term over here is length of the rod, which is L, plus radius of the disk to get to the center of mass. And you define everything with respect to the centers of mass. Now again, we're I kind of mentioned at the very beginning that you can have variable densities. We don't often deal with them, but it's kind of useful to keep it in the back of your head. But in this case, I have a very complex body, and this is a composite body. Okay. And I can solve through for it. So if I'm dealing with something like this, I would sort of look at it and sort of say x of bar for the rod and x bar for the disk. And what I'm interested in is where the center of mass of this object is, because you want to shift it from some arbitrary point to a point of interest. And in doing so, shift all of these values over. So x bar for the system is a weighted average, just like you did with a system of particles, but now it's two rigid bodies that are attached to each other. So you have mass of the rod plus mass of the disk, and the weighted average is mass of the rod times its distance from the point of interest, mass of the rod times x of the disk, and then you sort of calculate the x bar of that. Now in this particular case, y bar is going to end up being equal to 0, and it'll be mass of the rod, y of the rod, plus mass of the disk, y of the disk, so once you have all of that, you can sort of figure out everything else to deal with a system. But in addition, you can sort of say you should, at this point, absolutely know that for a long slender rod, it's 1/12 ml squared. For a disk, it's 1/2 mr squared. And for a hoop, it's mr squared. Just one second. So when I say you have to know these things, these are things that you wouldn't necessarily get that on a final exam. That's pretty much the only place where it matters. You should know these definitions, but the other thing to recognize is this hoop. And that hoop looks exactly like a radius of gyration, which is exactly what it is. Essentially, a radius of gyration is a way of distributing mass equally around a hoop and coming up with a number. Go ahead.
For the y component of the center of mass, should the denominator be m rod plus disk?
Yes. I'm sleeping. It's a long day. Today's going to be a really long day. I'm sure you're sympathetic. So out of this, you have two results. One for locations. You have these sorts of numbers or these sorts of relationships which you absolutely positively must have. And again, if you look at the crib sheet, you'll see them already in there. If you choose to do that your own way, it's up to you. So this is where we can start looking at kinetics. So say I have a rigid body. I've defined its center of mass somewhere arbitrarily over here. And what I do normally or every time I deal with a rigid body is I say, hey, it's got a mass of 10 kilograms, but that is all acting through its center of mass. As well, I'll define a coordinate system, and at the same time, I'll put a whole bunch of forces acting on it. Which is what you were used to when you dealt with anything to do with particles. You had forces applied to things because forces can push or affect a mass. But in addition, and differently, you're going to start to see moments. So here, for example, is a couple moment that's sort of acting on the rigid body, and it's acting to cause a twist. So clearly, you're going to have to start to worry about all of the motions that we talked about in the last lectures, and we need to first look at translation. So for translations, sum of forces is equal to mass times acceleration in the g direction, and sum of moments will equal 0. So that's nice. I kind of like these. They're easy to do. You don't have to worry about rotation. You do have to break these problems up. Again, is sum of forces equals mass times acceleration x, sum of forces y equals mass times acceleration y. We don't do very much with n and t. We can, and we can't. We don't do very much with r theta. I think we do a few cases. Not much. But the main point here is that you'll look at forces acting on a body. They'll cause an acceleration of the center of mass. We won't look at the acceleration of all the points on the body. So you already know that every point on the body has a different sort of potentially a different velocity, except in the case of translation. So the acceleration of the center of mass is the same here, 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 here. But there's no rotation. Then you have rotational motion. So in rotational motion, we're going to start to look at things that are just spinning. And so in those cases, again, sort of this, and again, I want to define something in here, a g, and I have forces here. I have a distance, and I have x and y. And the distance to these points is going to be r. So if I want to look at r in this body, it's just going to be x bar squared plus y bar squared equals r squared. All right, so I know what that is. I got that. So for a particle, you have forces, internal forces plus external forces equals mass times acceleration of the particle. If it's acting over some distance, that will equal r crossed MIAI. So you can take all of the terms, all of the internal forces, all of the external forces, add a moment arm to them, and then calculate each of their individual r sub i's. And you end up sort of saying that the moments are equal to mi, ri, acceleration of p, where p is the point I'm sort of looking at here, plus alpha crossed ri minus omega squared ri. So same thing as before. You've already sort of looked at these equations. You know that that's something you're going to look at with relative velocities. So you have the tangential acceleration, the normal acceleration, plus AP. So you're just doing a relative acceleration component for this. And R is equal to xi plus yj. And if you do sum of moments about g, you can add up all of the moments of everything, and they're going to be x squared plus y squared summed on all terms, and you'll end up with mg equals ig alpha. And this is going to be a crucial equation, and it's just like second law. It's a Newton's-Euler second law for moments. And with this term, you can say sum of moments is equal to ig alpha, and you don't have to do the integration for all terms on the body. You just have to do things with respect to the center of mass. And again, if you want to shift it to another point, you just have to shift it with the parallel axis theorem. So sum of moments about A is just ig plus mdA squared times alpha. And typical case that you look at for rotation is something like this, where you have a long slender rod pinned at one end, 1/3 ml squared, and you allow it to rotate, and you calculate what you're interested in. General plane motion. So I have a body, and it sort of undergoes some sort of motion. And as it's moving along, it's both translating and rotating simultaneously. So however it does it, there you go. Just some crazy sort of thing there. So sum of forces in x is magx. Sum of forces in y equals magy. And sum of moments about g equals ig alpha. Sum of moments about some arbitrary point alpha, or A, is ig plus ma times L over 2. So say, for example, I'm just looking at a case like this, A and G, that's what I would get. So I don't have to look at the translational component in that case. I can shift it all to A, and I look entirely at a rotation. And all I'm doing here is just adding that term. And so it ends up being equal to ig plus m times L over 2. This distance is L over 2, by the way. Times L over 2 times alpha. When you substitute in for A, so the translational A is equal to L over 2 times alpha in terms of just a scalar multiplication, and ig alpha. And the whole thing becomes 1/12 ml squared plus 1/4 ml squared times alpha. So sum of moments about G, in this case, would be 1/12 ml squared alpha. Sum of moments about A are 1/3 ml squared alpha. All you're doing with parallel axis theorem, and as long as you don't have slip and you don't have a weird acceleration or anything, is just translating a linear acceleration and making it into a moment, and from that, extracting out terms. So sum of moments about G, sum of moments about A. Any questions so far? All of this is definition, and it starts us on sort of the path towards actually solving problems. In the next lecture on Monday, I'll try and do that, but it's probably not a good idea to start anything today. Second term, sorry, which one? 1/3. That's a great looking 3. So 1/3 ml squared alpha, or, so all I'm doing here is I'm adding in 3/12 plus 1/12, I get 4/12 and 1/3. So that's, you're adding in terms, it'll become second nature after you see it a whole bunch of times. And you will have to see it a lot of times because that's what you're going to end up doing on the homework and in the course. Any other questions on this? I know you're very excited to learn new stuff today. All right. Good luck. I will see you at the midterm in 4 hours and 3 minutes. Thank you.